So let's look at an example. Let's let V and W be the same vector space. In particular, the polynomial space P sub 2. And we'll look at this under the standard basis. 1t t squared. And we'll define the following linear transformation. And this transformation definitely is linear because it's a differentiation. And differentiation is linear. Let's find the B matrix for T. And 2, let's verify our multiplication property. That the coordinate vector of T of P equals this B matrix times the coordinate vector of P. So, first part, this is pretty plug and play. We apply T to each of the basis elements. And then we need the coordinate vector with respect to B. So we write our result as a linear combination of these basis elements. And that lets us read off the coordinate vector. So there we are with the first basis element. The derivative of T is 1. So that's 1 times 1 plus 0 times T plus 0 times T squared. And that gives us the second coordinate vector. Apply it to the third basis element. 2t is 0 times 1 plus 2 times t plus 0 times t squared. So our coordinate vector is 0, 2, 0. Put these all together to get the B matrix. There's our first vector, our second vector, our third vector. Let's now look at the second question. So we want this coordinate vector to equal this product. So we need to get this coordinate vector first of all. So t of a sub 0 plus a sub 1 t plus a sub 2 t squared is a sub 1 plus 2 a sub 2 t. And because we're going to want the coordinate vector, let's throw in that 0 t squared. So this image, expressed in terms of this basis, is a sub 1 to a sub 2, 0. We want this to be equal to this matrix, which we've computed, times this coordinate vector. So I guess the next thing we need to do is compute this coordinate vector. Well, the coordinate vector of a sub 0 plus a sub 1 t plus some a sub 2 t squared is simply a sub 0, a sub 1, a sub 2. So we want to multiply this matrix by this vector and get this back again. Let's see. So our matrix times our vector. So 0, a sub 0, 1, a sub 1, 0, a sub 2. That is a sub 1, 2, a sub 2, 0. So that's right. Let's consider the implications of this. We have seen that any linear transformation from Rn to Rm can be thought of as a matrix multiplication, a matrix times a vector. What we're now saying is that any linear transformation from a finite dimensional vector space to itself, or to any other finite dimensional vector space for that matter, can also be thought of as a matrix times a vector. So this matrix represents the linear transformation of taking the derivative of a second degree polynomial.